So derivatives and integrals of hyperbolic functions. So we have all these formulas right here. Oops, I didn't need this. Here in the definition box. And you will find out how similar are these from the usual derivatives for trigonometric functions. The derivative, like the derivative of sine is cosine. The derivative of cosine, well, in trigonometry, the derivative is negative sine. Here we have a positive sinh. The derivative of tangent is secant squared. The derivative of cotangent, well, in this case is negative. So the difference in this case is that as opposed to the trigonometric functions, if you list the trigonometric functions in this order right here, the first one is positive, the second one is negative, positive, negative, so they alternate in signs when we look at their derivatives. However, for hyperbolics, in this case, their derivatives, the first three are positive, the last three are negative. And of course, we can see as well a very similar pattern right here for the integrals. All right. So I think that's the only thing that you need to memorize for this, that the first three are positive, the remaining three are negative, and not alternating. And well, of course, I mean, let's derive the formula to find the derivative of sinh. And of course, we can always use the definition of sinh, like in terms of hyperbolics. So, okay, what's the definition of sinh in terms of hyperbolics? Anyone remember?
E to the power of x minus e to the power of negative x.
E to the x minus e to the negative x over 2. All right? So, well, in this case, this is what we're going to do. Let me split e to the x over 2 minus e to the negative x over 2. And then we're going to take the derivative of these two terms. So that's y prime or the y dx. Your favorite notation is fine. And well, the derivative of the exponential is itself, e to the x over 2. And then minus the derivative of e to the negative x, which is e to the negative x itself, over 2 times the derivative of the exponential, which is negative 1. And in this case, well, this negative 1 times this negative 1 right here will turn into positive. And we'll put this together into one single fraction. And well, what's this? What's e to the x plus e to the negative x over 2? Isn't that cosh? That's cosh x. Alright? Of course, you can repeat this exercise for the remaining formulas. That's fine. But I think one example is fine. So how about we go ahead and look at some examples involving this derivative. So let's look at letter A. Let's differentiate x times sinh x of x squared. All right. Well, number one, which rules of differentiation do you think we should use to differentiate this function?
Would it be product rule?
The product rule is one rule, and of course the sinh rule and a mini chain rule. Of course, let's recall what the product rule is. Well, let me change colors here. Let's go. What happened here? All right. So the derivative of a product u v prime, again, is u prime v plus v prime u. Of course, if you use the letters f and g or Leibniz notation with letter d's for derivatives, I mean, it's the same. So in this case, the derivative h prime of x will be the derivative of x, which is 1 times the derivative times sinh, actually, simply sinh without doing anything, plus the derivative of sinh, which is cosh, with the same argument, x squared, times the derivative of the inside of the parentheses, because this is a composite function, so we are in the need of using the chain rule, which in this case is 2x. That times the u function, which is x. And of course we can simplify a little bit and clean up some symbols here. So that'll be sinh x squared plus 2x squared cos x squared. Final answer. Any questions about it? All right, how about you guys try letter B? Take a couple of minutes, have a look at it, talk to the person next to you, see what you get, all right? And then we'll look at it together. Of course, raise your hand if you get stuck with it. Alright, so in this case, let's have a look at this one. It looks like a chain rule will be involved as well as the derivative of cos, right? So, f prime of x equals, what's the derivative of a length, by the way, when we have a composite function?
Be 1 over cos.
1 over cos, so that is 1 over the argument, which is the quantity or the expression inside of the parentheses, times by mini chain rule sinh x. And in this case, well, if we combine these two together, what is sinh over cos? We can simplify this really nicely, actually.
The 10.
It's a tanh, right? Tanh x. I mean, of course, we could do, I mean, a lot of this. Of course, the same differentiation rules apply: product rule, chain rule, length, even implicit differentiation. I mean, everything can come up over here. All right, let's do an integral. So we have the integral of cos to x times sinh squared to x with respect x. All right. So, any ideas on how to go about this integral? I use substitution. So in this case, which one would be the u? The sinh. So typically we take u as, in a way, the most complicated part of the integrand. By most complicated part, we mean, number one, a quantity or an expression inside parentheses, a quantity or an expression inside of a radical, a quantity or an expression being the argument of a logarithmic function, or being the angle of another trigonometric function, or the exponent of an exponential function, regardless of the base. Well, in this case, we don't have this what's it called, parentheses. So let's make this look like parentheses. Sinh 2x, whoops, quantity squared, and times cos to x with respect x. All right, so I think that we add parentheses, it would be a lot easier to see and identify the u and set up and identify what part of the integrand will stand the du part of it. So, well, so in this case, let's set u equals to sinh to x. The derivative du will be cos to x times the derivative up to x, which is 2. I'm going to put that 2 in front as a coefficient, but don't forget the dx. All right. Well, in this case, what do we have? We have cos to x, dx, but we need a 2 here. So in this case, so that cos to x dx will be equal to 1/2 du. So we're ready to do the u substitution. So let's rewrite the integral as the integral of u squared times du. But that 1/2, I'm just going to write it outside. And then from here, let's just use the general power rule. Integrate. What's the integral of u squared? 1/3 u cubed plus c. But be careful to multiply these coefficients, these denominators. That's going to be a 1/6 times, in this case, u, which is sinh squared, to x. All right. Simple u substitution in this case, nothing really fancy. Of course, we're going to get to the integration methods in the next chapter, next week actually. Questions about this one?
Is it 2 squared or
That's meant to be a 3. Yeah. Yeah. Or an application problem. So so if we look at the graphs of these kind of hyperbolic functions, they give rise to these kind of curves. Yes, in a way they look like parabolas, with like really wide parabolas. If you compare the shapes, but the ones that we use for like bridges and chains like this in civil engineering and the design, they use the cos functions and the cos functions, and they usually call them catenaries. That comes, of course, I guess from the Latin root for the word for chain. So and hanging in there. So. And so the general form they use to describe this kind of change are y equals a cos x over a, where a is going to tell us the height of the cable. But the thing is, when we have an a being a negative number, we have like an inverted chain. It's an upside down. So let's have a look at this word problem. This very, very brief word problem. For the catenated form by the chain, and its form with a equals 12 inches, and the distance between the two posts is 4 feet or 48 inches. Be careful, because when it comes to word problems and when the units are involved, make sure to have a consistency with the units and have everything in either inches or centimeters, depending on the units, right? So that's why they're giving us the value in inches as well, so we can work everything in inches. So let's find the slope of the change at the point where the chain meets the right hand post. All right, so let's have a look. So they're telling us a equals 12. So let's write an expression for y equals 12 cos x over 12. So that's the function that we were going to work with. And of course, we need a little picture here. So let's see. Oops. So we have one post here, the other one there, and then as well This is 12 inches high, and the distance between the two posts is 48 inches. So be careful, because that's the distance from post to post. However, from the middle, that's going to be 24 inches. All right, so let's see. Let's just write down the units. All right, so well, all we have to do is, well, because they're asking us for the value of the slope, what do we need to do with the function in order to find the value of the slope?
2 points.
2 points. Well, that's if we were to find the equation of the line that is tangent, but we only want to find the slope. So which calculus operator gives us the slope, by the way? The derivative. So let's find the derivative. Y prime equals, so the derivative is 12 sinh x over 2, and what's the x over 12, what's the derivative of x over 12? Isn't it 1/12? All right. And well, notice how these cancel, these 12s cancel, leaving us with y prime equals to sinh x over 12. All right. And then we only need to plug in the value of x equals 24 to find the slope at the point where x equals 24. So y prime evaluated at 24. So that's a sinh 24 over 12, which equals sinh of 2. And of course, if you want to use the definition in terms of exponentials, e to the 2 minus e to the negative 2 divided by 2. Well, that'll be the exact answer in terms of exponentials. However, typically for applications, we use decimals. So let's go ahead and look and do that on the graphing calculator. Let me clear all this. So let's see, be careful when typing this on the graphing calculator, because in this case the numerator has more than one term. You want to make sure that both terms get affected by the denominator, and in order to do that is by opening parentheses. Second ln to get e to the 2. Was that a minus or a plus? Minus e to the negative 2. Close parentheses. Oops. And divide by 2. And that's 3.62. Typically we round this to decimal places, 3.63. All right. If you got anything different, double check your syntax here. Be sure to have the parentheses around both terms. All right, let's go back to, so that's 3.63. All right, so that's the slope. That's how steep it is at the point where the chain meets the post. All right.
Do we need to put inches or something, like a...
No, not in this case, because in this case it's a slope, so it's not a distance. All right. So okay, let's look at the inverse hyperbolic functions, and well, that's something by the way that I want to test you on. That's something that is just worth looking. In fact, I mean, I just brought the formulas here. I have a couple of exercises here to go through, you know. So, the reason why I would like to talk about this anyway is because, well, the regular hyperbolic functions are defined in terms of exponential functions. Well, so the fact that there exist These inverse hyperbolic functions, well, it wouldn't be a surprise that they would be defined in terms of their inverses of the exponential functions, which are logarithmic functions, right? And well, again, this is something you don't even have to memorize, you don't have to look at. Just this is something that you will look in higher levels of mathematics when you get to complex analysis or special functions. When you solve other methods of solutions for differential equations. I have some exercises here. I'd rather just skip them because ultimately I won't test you on it.